Welcome, everyone. Welcome, everyone. This is the Openscapes Community Call. A welcome to NASA Earthdata and earthaccess, and we're so excited that you're all here. This doc that we're screen sharing is being posted in the chat, so you can follow along as well. And we are now recording this session, and we will be posting the recording on YouTube. So we'll plan to pause the recording when we're doing group discussion. Live transcripts are available as well. We are so excited that you're here and that you're here to learn about earthaccess with us. The NASA Openscapes mentors and the Openscapes team are here on the call. They're listed here, and you're welcome to reach out to any of them. We'll all be looking in the chat, and we'll be interacting together today and tomorrow. All Openscapes events are bound by our code of conduct. And to summarize some of these points, it is that we ask that you're respectful and value each other's ideas, styles, and viewpoints, and lead by example and match your actions with your words. If there's any problems, please DM me and I will be responsive. Our plan for today is that we're going to have a community call today, 3 hours. We'll have a break at the midpoint. Today's format is presentations and discussion. We aim to be joyfully strict with timing and invite you to follow along with the agenda and also to ask questions in chat. And we'll be pasting the questions into the doc so that folks are able to then see them all in the doc here. Based on the number of registrants, we thought that the Google Doc would break if everyone was editing today. So that's our little system for today. But we'll be also facilitating this whole call in an open way. So you'll see us updating times and helping each other out as we lead. And there's a link to the slides for all the presentations today. Tomorrow's coworking will also be 3 hours and we'll have a break. For that, it is come and be prepared to try things hands-on, learn from screen sharing with others, go into breakout rooms and see live demos, and be in our Jupyter Hub coding along in earthaccess and trying things out and working and asking questions from NASA experts and earthaccess developers. So please, those are the formats for these 2 days. All of our resources and future events will be updating on the NASA Openscapes website, so please check back there. And just wanted to acknowledge that there's a lot going on right now. We're a group of NASA collaborators who were still working during the US government shutdown. However, today the government has reopened and many of our federal colleagues are back, and we're just this community trying to support each other and teach earthaccess together. And we're really excited to all be here and to be leading this event with you all today, and really appreciate that you're all here as well. So I am going to give a quick intro to what is Openscapes and what is NASA Openscapes with my colleague Amy Steiker, and then we'll get into the rest of the program. So I'm going to share these slides that you're also able to follow along on. There's a lot of links throughout all of these slides, so feel free to follow along on your own computer as well. But we often get the question, what is Openscapes and what is NASA Openscapes when we lead events? So we wanted to answer these questions together. So we think about Openscapes as co-creating science infrastructure that's open in kind. And we really think about this both as technical infrastructure and social infrastructure. So I'll share a little bit about how Openscapes as an idea and as a mechanism and an organism, and then Amy Steiker will share about NASA Openscapes and how this is this team enabling science across the NASA Earthdata world and building really kind, impactful solutions from, with, and for Earthdata users like yourselves. And that includes earthaccess. So Openscapes as a word is something I came up with in 2018 as a feeling of welcome and empowerment around data-intensive science. This is something I felt from the open source software community, particularly the R community. And I was interested in supporting other scientists like myself in this feeling of welcome. And so Openscapes has become a mechanism to solve these technical barriers, these social and organizational technical barriers to modern workflows. And we've been working with many different groups since 2018, sometimes through the Champions program, as you're all here today. And we also work with many large organizations like NASA Earthdata, like NOAA Fisheries. And we're also now a small organization as well. And so we have a small core team that supports and collaborates and forms deep partnerships with our collaborators at these different groups. So what we do as a small team is we work with organizations that want to make change, and we help support that change, whatever that change might be, using a mechanism that we've developed and iterated called the flywheel, where we help bring groups together and identify and solve the challenges that they come across, so that then awesome teams can lead change in many interwoven ways. And that's what you'll see the NASA mentors today sharing about, all this real change that they've been leading together. So hand off to Amy, I just wanted to say that what the NASA Openscapes mentors have done is really that the NASA Earthdata has a 5-year track record of successful and collaborative cloud trainings. And these mentors that you'll hear from today have been supporting Earthdata users and doing so really efficiently and with less maintenance burden on the teaching and development side, because they've been working together so beautifully. And they've also been solving previously unseen gaps. And so you'll hear about that today through earthaccess and the Cloud Cookbook. I'll pass it over to Amy Steiker.
Thank you so much, Julie. Really appreciate that sort of introduction on Openscapes and NASA, the NASA Openscapes effort. So just diving in a little more deeply into NASA Openscapes itself. So this is an effort, really truly a movement and community that started in early 2020. And we had and continue to have this primary goal of teaching and supporting researchers' migrations to cloud computing workflows. Michele Thornton, who's here, will be also speaking more to a little more background overall on the NASA Earthdata effort to move and migrate data into the commercial cloud. So you'll hear more about that. But as that was happening, we really identified this need to be directly working together alongside our user communities to kind of figure out what this means in terms of the research workflows that our users currently have. So this is across a DAC effort, across several different NASA data centers, and we really are kind of in the middle where you see this Venn diagram. So we have this incredible, diverse background and skill set. We are software engineers. We have scientific backgrounds. We practice and promote open source and open science practices, and together we are mentoring and teaching and empowering our user communities. And this is a great picture of us from 2023. Again, we started in early 2020, right as the pandemic and lockdown had started. And this was the first opportunity for us to be together in person, and really powerful, as you can see a couple of the mentors who are here today with us in that picture. Next slide, Julie. So just a little more background. You can see so many people who have been a part of this effort across this over 5 years where we are today. Just digging in a little more deeply into this, again, this higher level goal of supporting you all in terms of your analytical workflows and understanding kind of what cloud may mean or may not mean to you. Some of the things that we've been doing as a part of this effort have been co-creating common tutorials, reviewing, reusing materials together. That's been such a common sort of way in which we work, is reusing, forking, iterating. We are a community of practice for teaching, mentoring, and facilitation. And the other big component here is that we've been scaling. So through these engagement opportunities, we have been scaling not only within NASA Earthdata, but also working with the larger community to scale as open science leaders as we've been teaching these concepts. And this is just a snapshot of some of the incredible work we've done throughout the years, over 30 workshops, 50 talks, and then as we'll get into with our cloud computing environment, So far, just this year, we have over 500 users who are working this environment. Again, we'll go into more the tooling later on today, and over 900 distinct users ever who are utilizing some of the tools that we have been building together to facilitate the ways in which we work and to facilitate this change in workflows and the teaching that we do. So next slide, Julie. A little bit more as far as what open looks like, and this is, I think, a really great diagram to kind of show how the ways in which we've worked through this open model, learning together first within our own Openscapes mentor community, how we've been infusing that across different sort of layers and levels of communities across this whole landscape of Earthdata and beyond. So this is us at the top in gray, learning together first. We've then been kind of teaching, like having peer teaching and documentation and onboarding of other mentors within our NASA Center staff. So that's kind of what's in light blue. Again, then infusing that knowledge and working alongside our end users and you all on teaching users directly. So this Openscapes Champions today and tomorrow, this is sort of a consolidated program that we have continued to utilize in the past. So this is where we get to know our users more deeply. And then finally, connecting and sharing that knowledge and, again, the ways in which we work to the broader open science community. Next slide, Julie. These are just a couple of the outcomes, both in terms of more on the technical side and the tools that we'll talk about today, also in sort of these some of the engagement opportunities and events like Champions, as we talked about, what we're doing today with you all, other workshops and events. So Celia will talk more about our NASA Earthdata Cloud Cookbook. This has been a huge part of what we've done and co-created together. So we'll share more later on today about that. The 2I2C Jupyter Hub is where we will be interacting as we both later today and tomorrow in terms of spinning up a cloud environment that's shared where we can teach alongside you all today. And then finally, earthaccess, of course, which is where we'll jump in more deeply later. So that's been a big outcome of this effort as well. Yeah, next slide, Julie. And so, finally, it's my final slide for now. We will talk more again, we'll dive into more about earthaccess, but this upcoming event, and the idea today with this Champions 2-day event is to hopefully be sort of utilized as an introduction and maybe a jumping off point and pathway towards more engagement into this earthaccess Python library community. So we have another event that's coming up next month. This is a hybrid event that's both in person, it's alongside AGU, but it is not a part of the event itself. It's independent of AGU, but happens to be coinciding in time. Again, it's hybrid. There are many ways to contribute, and something we want to really drive home today, and we'll keep emphasizing, is that your questions, experience, and backgrounds have led to the creation of this library. They continue to be critical as far as shaping and growing it. So we welcome all contributors. You do not have to be software developers to engage in this event. We have various tracks, and we can share out the link to this registration, but we'll keep coming back to it, but want to get it out here first and foremost, so that you're aware of this event. We'd love to see you there. All right, that's it for me for now. Thanks.
Great, thanks, Amy. And next, Michele Thornton is going to share about welcome to NASA Earthdata and cloud computing. And Michele, would you like me to keep sharing, or would you prefer to?
Sound check, Julie. Okay.
You sound great.
Awesome. Yeah, if you want to keep sharing, I'll just do a next slide.
Perfect.
All right. So hello and welcome, everybody. It's so exciting to have you here. It's so exciting to have my colleagues back who are back. So welcome. So my name is Michele Thornton. I work at the ORNL DAC. ORNL is the Oak Ridge National Lab in beautiful East Tennessee, and we're glad to be here. I have the task of just giving a pretty high overview of NASA Earthdata and cloud computing. So what is NASA Earthdata, and where is NASA kind of moving for cloud computing is what we'll talk about. Next slide, please. Yeah, so NASA Earthdata, if you're not aware, there is a very big activity going on right now, and this website represents a lot of that, just earthdata.nasa.gov. And this is really your entry point into NASA Earthdata. Not only data, but just a myriad of resources. As far as project pages, NASA Earthdata project pages, NASA Earthdata search, which is driven by metadata, and lots of catalogs and tools and services for accessing data. So I mentioned that there's a big effort going on that we locally know as web unification. And so if you're familiar with the data centers or the DACs, again, I'm from ORNL DAC, the unification of NASA Earthdata has been going on for several years. It's still ongoing with the ultimate goal of having all NASA Earthdata discoverable and distributed by this unified website. So as a user, we often hear that it's difficult to find NASA data. Some of the tools and services are pretty spread out. And so this is a big effort, and we're all very excited about it. And it's really leveraging and helping the user community out. So yeah, a little bit more about NASA Earthdata with the next slide. We often share this slide, the Earth fleet, just to introduce all of the orbital missions that are NASA Earthdata. So this circle spiral around the Earth are past, mostly still operational satellites, and that NASA is downloading those raw data and then processing them through to some level of data set. It might be, reflectance. It might be a higher derived product. There are active instruments, passive instruments. So a lot of data here throughout NASA's history, of course, of building, launching, maintaining satellites, and providing data free and accessible to the public. So that's a look at the orbital missions. And then the next slide is a look at NASA's fleet of airborne platforms. So NASA has a very active and robust Earth Science Airborne program. It has a wide range of airplanes, aircraft, and other platforms that fly just a very broad variety of instruments. Again, active instruments like LIDAR and radar, in situ instruments that collect grabs of atmospheric profiles. You can see some of that graphed in the on the left bottom slide there image. But just a window into the idea that NASA doesn't just have satellites, that there's this really active airborne program, and all of that data also is part of the NASA Earthdata collection. And then the next slide, please. And with that, so we're going from these orbital missions to airborne missions to field data, and NASA supports just a wide variety of field experiments and has for years, and it's often looking at scaling issues or the orbital and field data are used to calibrate and validate satellite data, as well as just understanding the Earth system processes as a whole. And that's a very broad program from, you can see some oceanic activities, field measurements all over the globe. So a very active program. And of course, these data also are part of the collection of NASA Earthdata. And the cost and the human resources of these important data collections can't be overstated. So it's volume-wise, not always the biggest volume of data, but to have those in situ and field observations are just really critical to understand a lot of the scaling and to validate and calibrate instruments on the aircraft and what eventually end up in orbit. Next slide, please. And so just to kind of wrap this up into one mission, so this is a mission that's active right now, GEM-X. It's the Geological Earth Mapping Experiment. It's a very interesting mission happening with a collaboration between NASA, who have the platforms, the instruments, and USGS, who really have the expertise in mineral imaging spectroscopy. And so there's an active campaign right now flying the ER2 aircraft, which flies at 70,000 feet, so almost out of the atmosphere, and flying 3 instruments: AVIRS Classic, AVIRS 5, and Master. All of those are passive and at some range imaging spectroscopy to multi-band images. But associated with that and is EMIT, which is that picture of the International Space Station. So EMIT is an important instrument that is on orbit and is providing kind of as a secondary objective, also imaging spectroscopy that is applicable to the GEM-X objective, which is to map critical minerals across the Southwest. And with that, there's a person out there in what looks like a pretty dry area doing field spectroscopy. And so, this is one mission that really ties in the field, the airborne, and the orbital missions. And it's very often that NASA airborne and field campaigns are complex, and all of this data, again, going into NASA Earthdata. Next slide, please. So I am, and a lot of the NASA mentors here work at one of the many NASA DACs. DAC stands for a Distributed Active Archive Center. And these centers, our jobs are to, if it's orbital data, have that processing stream robust and available for satellite missions. Most of the data that we get at the ORNL DAC is airborne and field data, so a little bit different workflow. But the same objectives to standardize data, to make it fair, interoperable, reusable, machine readable, able to be accessible through NASA enterprise tools and services, and also to provide the standard level of metadata for collections and right down to every single file having metadata that is consistent across NASA Earthdata, so that those data are discoverable through a lot of the programmatic access methods that will be talked about later. the DACs have operated as an enterprise solution within Earthdata, but through the years they have developed a lot of tools and services and had individual distribution methods that my little researcher up in the upper right corner there with the question marks above their head it's often a challenge for somebody who's kind of from the outside, and even if you're kind of on the inside, it's a challenge to go to 11 different data centers and figure out who has data, what's the tools and services that are available for that data. And so I mentioned this idea of web unification and cloud computing, and that's what this is solving is a user having kind of a one-stop shop for all of NASA Earthdata and the compute resources behind that. So we'll dig into that a little bit more. Next slide, Julie. So again, the idea here that even through one campaign or all of the NASA campaigns that are funded, that orbital data will go to one DAC, airborne data might go to another data center, field data might go to another data center. And that work is still happening. All of that standardization, all of the quality assurance, all of the metadata is still distributed throughout the data centers. But all of that data is now going into Earthdata Cloud and is accessible through Earthdata Cloud instead of individual DAC distribution endpoints. So next slide. Oh, so yeah, so this is, I think Earthdata Cloud, cloud seems so dark and heavy, but this is really the sunshine and the sort of happy place, I think, for researchers that the Earthdata Cloud provides us. Yeah, so it's not dark and gloomy. It's a happy, sunshiny thing. Next slide, please. Yeah, so what is Earthdata Cloud? And so starting over on the left-hand side, again, NASA's cloud-based archive of all of its Earth observations. I will say that not all data centers, not all DACs have migrated to cloud. And so when you go onto NASA Earthdata, you'll see a little banner that says that is still in progress. But it's within this year, I think all data will be migrated to NASA Earthdata Cloud. It is hosted by Amazon Web Services or AWS, and you'll be hearing more about that. Up on the top there, so some of the what this enables, of course, is open source is part of the NASA Open Source Science Initiative. That's a broad initiative across all of NASA. Data are co-located. You don't have to know where to get data. The cloud compute and what we'll be focusing on these next couple of days allows analysis in place. And so a lot of the workflows of download data and then analyze, if it's appropriate, if you're able to, you can spin up an environment, do your analysis in place, and really reduce the burden of downloading data and trying to deal with some of the really big data sets that NASA has. And then there's also the common Earthdata tools, like earthaccess is definitely something that you'll be hearing more about. And then this enables multidisciplinary science for data users, and of course that's a huge benefit. Next slide, please.
I think that's.
Is that me?
That's it. Thank you so much,
right.
Michele.
Great. Yeah. Okay. Thank you, Julie, and thanks for the opportunity. I hope that helped out to give an introduction.
That was super. That was super. And we have a few minutes for discussion if folks have any questions or want to unmute, since we're a smaller group. I see Alexi's in the chat says, I'm in love with all this information and good news you're sharing with the scientific community. Thanks. That's a wonderful comment. Thank you.
I think, as they say, the devil's in the details. So
Provided
start diving in.
First layer, which is so great.
Yeah.
Do any of the mentors have a question? Oh, sorry,
I wanted
Seth,
to share another comment from the chat. Martina says, as a student in data science, this makes me excited. And that sentiment is wonderful, just like, you know, the sunshine you had there, Michele. And I'm curious, when people say, I'm excited about this and this is great, I'm curious if people could say more about what it is that you're thinking that's exciting, not to put anybody in the spot, but certainly when we run these NASA Openscapes events, you know, this is like a kind, welcoming, safe space to ask any kind of question, whether it's like really beginner or really advanced. The folks, the mentors here are really keen to help you get what you want and what you need or what you're curious about. So please don't hesitate. And then Julie was suggesting that maybe some of the mentors had questions or things they wanted to raise from Michele and Amy's presentations.
Thank you. May I ask?
Yes.
Yeah, so my name is Alexis. I am in Colombia at this moment. I just graduated from the Ohio State University. So the good news for us here in Colombia is that we can use all this material to teach and to replicate all that knowledge to our people here. So I'm seeing here all those notebooks that are available here. And then I have some students, they are asking where we can go to study, which materials, which course or online course do I have to pay? But we don't need that. So those are the good news, that we have there the data on the cloud, the notebooks, and yeah, all the platform that you are providing for us. So thank you for all the work that you are doing. And yeah, that is my point. That I want, the thing that I want to share with you. That's why we are happy with you. We are in love with you.
Oh,
Thank you so much for those kind words. You know, and we'll keep trying, and we love the feedback, and you know, any constructive criticism or needs are always welcome. So yeah, don't be shy.
great. Well, thank you so much, Michele, and thank you, Alexi, for the comment. Michele, let's continue along, and you'll grow more questions and comments and ideas as we go. So we'll have more times for discussion after each presentation. And Amy is up next. Amy, would you like me to continue screen sharing, or do you want to? What would you like?
You are welcome to. Since
Great.
it's already up, why don't we go with that? Yeah, no problem at all. Great. So yeah, and I'll just introduce myself. I know I just spoke, but I just want to mention that yeah, I'm one of the NASA Openscapes mentors. Of course, I am at the NASA National Snow and Ice Data Center, DAC, one of the DACs that Michele just introduced. I'm really happy to be here. I've been a part of the Openscapes mentors since the beginning in 2020. So we're going to dive in now to start talking about the earthaccess Python library in more detail. So I'm going to give an overview and talks really specifically though about the ways in which we work within this earthaccess Python library and how this has really been accelerating NASA Earthdata as a whole and that access, again, through the ways in which we work through this open collaborative development. So that's really where I'll focus today. And I'll also mention before you go on the next slide, Julie, that this is sort of, again, this is an intro, more of a presentation, and then right after this, we will dive in. Mikala will be doing a live demonstration of earthaccess, getting everyone set up to start utilizing it yourself. So So yeah, I just wanted to point that out. But go ahead, Julie, can dive in. All right, so first, jump into the what. We mentioned it, it's in the title, we're talking a lot about it. What actually is it? So if you go to the next slide and click play on the video, this is a pre-recorded video, and I'm just gonna run through what this looks like. I'm utilizing Python right now. I'm importing 2 libraries, that's it, importing earthaccess, importing xarray. Now I'm logging in one step, earthaccess.login. So that's through Earthdata login. Again, Michele will talk more about that. I'm now interested in a particular data set. So this is a PODAC landing page. I'm setting that data set DOI and setting that DOI object. And now I'm going to search for the files within that data set using earthaccess.searchData and setting a results object. So I'm going to specify the DOI that I just found through a NASA Earthdata landing page. I'm setting a temporal range of interest. So within that data set, let's say I'm interested in 2 months of data over the summer months in 2022. So I could set that again to kind of filter down the data that I'm interested in within the data set. And now I'm just going to print out the first 5 results. So what it found total were 12 granules or files. And this is all the metadata that is contained within those. So it includes links to the data access itself. Now I'm going to utilize xarray, which is a common geospatial Python library, and I'm going to put those results directly into xarray, and I'm going to open a multi-file data set utilizing earthaccess.open. I'm doing this streaming, so I haven't downloaded any data. I'm working within a cloud environment, so there's no intermediate step. Now I have all the data loaded into a single xarray data set for further analysis. But I can take that same results, and let's say I do want to download the data. I can take the same results and use earthaccess.download and set a path on my local computer, just in my current directory. And now it's going to download those files to my drives, and these are NetCDF files. So super quick, in 2 minutes. Again, Michele is going to actually show this in more detail with a slightly different workflow, but that's a real quick introduction. Go ahead, Julie, go to the next slide. All right, so that kind of answers the what it's doing. It's searching and accessing data in really just 3 simple steps. How did we get to this point? So now I'm going to jump into kind of the origin story of this Python library and the connection between earthaccess and NASA Openscapes. So something I do want to point out, we showed hey, look, a couple easy steps to find some data files of interest and start working with them in a Python environment. Before this was developed, though, I think something that I really want to emphasize is that this was actually quite difficult to do before the library existed. And in the context of NASA Earthdata Cloud, as Michele mentioned, the devil's in the details. Some of we identified a couple of challenges as this migration was taking place. So we mentioned there's a lot of independent systems across NASA data centers, right? As Michele mentioned, lots of different tools and access methods. So that we had to kind of figure out and format each of those search terms across those different systems. Credentials, so I mentioned Earthdata login, Michele will cover that more, but there's even an additional credential layer that happened with the move to Earthdata Cloud. I didn't mention any of that in the last slide or video, and the point is that we wanted to make that as transparent as possible. And then creating separate workflows for in-region versus download. So what does this mean to work in place? Well, we wanted to make it as simple as possible. Like I mentioned, same results that we got back in that second search data set step, we could utilize that whether we're working in the cloud or not to download or work in region. And then just having to kind of interact with cloud-based storage and figuring out what are these new concepts. Again, trying to think about how to make those as transparent as possible. So if you want to advance, Julie, now with earthaccess, as I just showed, it makes this all much more seamless. 3 of those basic steps: to log in, to search for your data, a couple different ways to do that, and then access the data and really just get moving as quickly as possible to do your analysis, which is really what this is all about, trying to really enable that science. So there really was this chasm between users and NASA Earthdata Cloud. Okay, next slide. Back to the origin story, though. How did we get here? How was this library built, and what was the background? So kind of answering this why now question. So that's again where we connect back to the NASA Openscapes effort. So again, this mentor team across our DACs co-creating and teaching these tutorials, as I already mentioned. So earthaccess really came about and was developed initially through NASA Openscapes. So if you go to the next slide, Julie, I'll talk about this in a little more detail. The key point here, the key sort of ways that this library was enabled was in this co-learning and the events that we had developed through these hackathons and tutorials, really starting up several years ago. So this 2021 Cloud Hackathon that we developed, where we were teaching the cloud, similar to what we're doing today, and receiving feedback from users. So getting these responses in terms of how these tools don't seem quite mature enough. There's this very complex tool chain, as I just mentioned. It seems very complex. So we got that feedback. The advanced Julie, we were able to take that feedback and started a prototype library. So back then, this was back in 2022, the Python library was originally called Earthdata. We rebranded that to earthaccess and started to teach it. So we took that feedback and thought, hey, we can make this easier, right? With all the components that I just mentioned, how can we abstract some of these complexities? So this was really great initial feedback, hey, earthaccess, this is a nice improvement over the ways that we had to learn about, again, these new concepts, these new intricacies of this commercial cloud and all of the new concepts, and also language that kind of goes along with that. So really great initial feedback. Next slide, Julie. So that's a little bit of how we started and how NASA Openscapes enabled the initial development. So now where we started, and also where we are today, is we approach this library in really strongly as a community first library and project. So I want to cover some of the barriers, or how we've reduced some of the barriers to enable the growth of the library itself and to continue to improve it. So next slide. So we keep talking about kind of this primary goal of NASA Openscapes. We want to support users migrating these analytical workflows to the AWS commercial cloud. What we've realized as we've developed the library is that it's so much more. And I just want to highlight a couple of things here. I recognize, I'm not going to go through all of these acronyms. You don't need to know all of these in particular. But what this is showing, this is just a star history graph. So it's showing in our GitHub repository, if someone is interested in the library, they kind of want to star it as, hey, this is great. I star it, I like it, I want to come back to it. That's kind of a metric that we've used and seen just really continual growth of that. So it really is analogous to the interest that the user community has, and and sort of the positive feedback too that we've been getting. But the contributors, if you look at all these pictures or GitHub profile pictures, this is showing all the people who have contributed to the library. And I think something we really want to emphasize is that this is not being done in a closed vacuum, something that's sort of proprietary or only for those of us who are funded or work directly with NASA Earthdata. All of these organizations, while many of them are some of the NASA distributed active archive centers like NSIDC, ASDC, again, a lot of those acronyms here, there are folks, first of all, at NASA headquarters, so also at NASA, but beyond the DACs, of course, Openscapes, but several other contributors who are outside of NASA. We have folks from the USGS, US Geological Survey, other commercial companies like Coiled Development Seed. So this is really just, again, emphasizing that that it takes a village, and this is, again, something that we want to continue to enable. So next slide, Julie. So I think a key piece of this, in terms of, all right, how has this been truly open, and how have we been able to do this development sort of in a community first way and fully open? And I think this is a really common core theme even within Openscapes, but we've been utilizing it in earthaccess as well, that there's this really important feedback between the technical and the social infrastructure, where you have people, the teams and community kind of doing the work, and then also the tooling to kind of enable that. And again, they kind of go hand in hand and work off of each other. So for example, like I mentioned, some of the early workshop feedback, that has helped to to identify some of the priorities that we have in development. And again, this is something we want to hear from you today and tomorrow on as well. How can this shape kind of where we should go? How we can improve. We also have bi-weekly hack days. I'll plug that in just a minute. We have asynchronous opportunities for asynchronous discussion, and that these tools and community evolve together. So if you want to advance, Julie, just wanted to show kind of a couple of examples of that, where on the people side, we have ways to engage through various mechanisms. Slack, recently we were utilizing Zulip, which is an open forum for chat, where you can add discussion topics and sort of discuss amongst the community. And then we have these hack days, again, I'll mention them in a minute, but ways to engage and actually, meet people and learn from each other in a synchronous way. And then things like some of the tooling and practices, we're going to cover these later on today, and we'll show and demo them and work with you more tomorrow on some of the other open source projects that we have been collaborating with to do some really cool, innovative things with earthaccess, again, that we'll share in more detail. Next slide, Julie. Yeah, so really just want to drive home the point that we have sort of built this library with intentional culture and community. We feel that that's been really critical to its success and future growth. And this is really a call for, as you learn more about the library today and how to work with it, that you are already contributors today when it comes to hearing from you. What do you like? How can we do better? So we really want to work on ways to amplify that and encourage more engagement. So this really just drives home some of the points I already made as far as the open community, some of those community partnerships. Again, we'll kind of cover those and weave them in as we go throughout this event, and again, some of those workshops and engagement opportunities like today. Next slide, Julie. So just moving forward, yeah, you could advance. Just want to share a few more slides, but we'll cover more of the sort of innovation side of things later on. But I love this slide. Luis Lopez, who is our core developer on earthaccess, he put this together. And what I love, so Patrick Quinn, he's a former architect of NASA Earthdata, which is the program that kind of sits above all of the NASA DACs. And I sort of coined this, this phrase up top: stop building tools, start fixing data. And I think where we really see earthaccess is fitting into the larger kind of ecosystem of NASA Earthdata, really of earth science data in general, is kind of starting at the bottom. That earthaccess, we keep looking at earthaccess as a way to kind of bridge the gap between kind of issues with data, maybe quirky, metadata issues or things like that, things that make it challenging to just start working with data right out of the box. This is really where we see ourselves to make it, again, as simple as possible to just get the data you need, start working with it as quickly as possible. So that kind of feeds into and can be, again, used as sort of this bridge as our data producers kind of continue to shift and focus on, fixing kind of foundational issues, making data as Michele mentioned, as fair, as, reproducible, accessible as possible. Next slide, Julie. So just, yeah, so this really just drives home the point. I wanted to show it again, this awesome image that Julie shared talking about Openscapes itself, but we really see earthaccess as part of this broader landscape on reproducible science. So yeah, with earthaccess being, we are able now to have a very reproducible workflow that can be shared. And so that's just a really exciting thing for us to kind of fit into again, this larger movement. Next slide, Julie. Yeah, so finally, just a call to connect with us. I mentioned these bi-weekly hack days. I also mentioned our bigger event coming up next month. That's a full day hack day event. But we do every 2 weeks. We come together and meet. We welcome everyone, new contributors. Again, you do not have to have a software development background. You could be brand new and just kind of want to learn what's going on. We can guide you to the right people if you are interested in being in contributing in small or big ways. So we can share more about that. If you're interested, you can kind of say hi in our GitHub announcement and we can get you added to the invite. And I think that is it. I forget if I have one more slide. I think that's it. All right, thank you.
Great. Thanks so much, Amy. Yeah, that was a super intro to Earth Access and all of the history and future. I love it. I am wondering if folks have questions or what questions folks have for Amy. There was a question in the chat a bit earlier that has a conversation around it. So I don't know if you, Amy, want to look at that and comment at all, narrate, or if there's other questions. Yeah.
Yeah, and of course, I mean, if we want to have more of a discussion too, that's fantastic. It's a great question on GEE, which is Google Earth Engine. And yeah, it's great that some folks already responded. I think one thing out of the box that comes to mind too is that Earth Access today is a Python library. As we show in this slide, it can be installed via pip or conda for those who are familiar with those install methods in Python. So, we're really looking at this within a Python-based workflow. Google Earth Engine, has an interface kind of tied to it. I know there's other backend scripting. I'm not as familiar with Google Earth Engine as I am with Earth Access by any means. But so that's, I think one thing just off the bat that I wanted to mention is it's, we're talking really within a Python ecosystem. We've talked a lot about expanding and supporting other, not only programming languages, but thinking about handoffs or how do we use this in conjunction, maybe with other tools like Google Earth Engine. So I'd love more thoughts and discussion on that, but that's just something I guess I wanted to mention first and foremost.
Thanks, Amy. Are there any follow-up comments to that? You're welcome to unmute for folks that have been in the conversation already in chat or otherwise.
This is Andy Barrett. I just add that Earth Access kind of allows you to work anywhere. You can work with it locally on your machine. You can work with it in a cloud instance like AWS. It doesn't matter where you are. So you're not tied to a single provider for using it. So that's kind of one of the key differences between that and Google Earth Engine, where with Google Earth Engine, you're working within Google Earth Engine. So I think it's a huge benefit.
Thanks, Andy. Other questions or reactions at this time? Right, I think people are ready for Mikala's live demo, and then there'll be more, even more conversation. So if that sounds good to folks, yep, Mikala.
I'm ready.
Are you ready? Would you like to screen share now, or do you want to hand off later on?
You keep control for
Okay.
now, if you don't mind, and then I'm gonna hop right over to my my Jupyter Hub instance. So that makes it easier for me. And I don't have a lot of slides here. So if you go to the next one. So my name is Mikala Beig. I work at the National Snow and Ice Data Center in Boulder, Colorado, and so one of the NASA Data Archive centers. I work in user services, and which is a lot of fun. And our whole job is just to help folks gain access to NASA Earth data and help facilitate that and make it as easy as possible. So, yeah. So today, I'm going to give you a little first intro demo to the Earth Access Python library. I think of it kind of as a quick start. It's pretty fast workflow. I'm going to be working in this Openscapes Jupyter Hub that's managed by 2i2c. And if you guys join tomorrow for the co-working, you'll be able to get access to this as well through a shared password. So you don't need to know any of this right now, but just a little sneak peek intro for tomorrow. So yeah, next slide will be good. Just a reminder for folks, so if it's something you need to do today and prep for tomorrow, all NASA Earthdata access to the data require an Earthdata login. And so all the data are freely accessible to everyone, but you have to register for one of these first. So if you haven't yet, go here and you can do that. And it's really quick. Tomorrow, just a couple of slides. This will be more for tomorrow if folks join me for doing this demo again, and you can follow along and we'll do it together. This is what it will look like when you log in to the hub, and we'll be giving you a password. Yeah, next slide. You log in, we're gonna choose our resource. Next slide. And it'll takes a few minutes to set up, so we'll have you get that starting up then, and yeah, and that's it. And I think there's one more slide, but yeah, and then we'll be working in a Jupyter notebook tomorrow. So, all right, I can take over then and get into my hub space if that works. All right, tell me if you're seeing a Jupyter notebook.
Yep,
in it.
and it looks good.
Okay, font size looking good.
It could maybe be a little bigger. What would it
Okay.
look like a little bigger?
Let's do one more. Hang on. Get in here. How's that?
Great.
Yeah, it's
Thanks.
huge for me, but I know some people are on laptops. And all right. Okay, and sorry, my camera's on my laptop, but I'm working over on my monitor, so I apologize if it's like I'm not looking at you all. Okay, so yeah, we're gonna start with the demo. You can see this Jupyter Lab environment that you might be familiar with. I'm in the Openscapes shared Jupyter Hub right now. I'll be working in a notebook, a Python notebook. Yeah, and I'm gonna demonstrate 4 of the most useful functions of earthaccess. These basic steps, the first thing we're gonna do, and this is very similar to that quick video that Amy showed us earlier, and I'm just gonna do it way slower and actual typing. So you'll just have to bear with my typing skills. All right, so the first thing we're gonna do, we're gonna authenticate using our Earthdata login credentials, and we're gonna use an earthaccess to do that. We're going to do a little search and discovery within the NASA Earthdata archive for data sets that match a specific keyword search. We're going to search for some files within a particular data set. I'm going to choose one for us, and we're going to use a spatial filter to narrow down our search to data that falls within a particular geographic area and temporal range. And then we're going to access the data. And in this particular data demo, I'm going to demonstrate using earthaccess to download some files, and they'll download here into our local Jupyter Hub instance. In later demos, you're going to see how powerfully and simply earthaccess enables direct cloud access or streaming of data, that earthaccess.open that Amy showed in the video. And you can access the data without the need to download, but we're going to just access a handful of files in this demo and go ahead and download them here. So let's get started. So the first thing we need to do is import packages that we'll need. So most importantly, we are going to import earthaccess. I'm also going to import a little helper library, this pprint or pretty print. And I'm just doing that because later I want to show you some metadata, and this makes it a little bit easier to see. So a little more human readable. So, all right, our first step, we are going to log in or authenticate using our earthaccess credentials. So I'm entering my username. Gotta grab my password over here. Can't see it. Okay, phew, that worked. All right, so we are authenticated. So yeah, that was step one in our four basic steps. And the next thing we're gonna do is we're gonna make a query for collections. NASA jargon refers to data sets as collections. So sometimes you'll hear us use those words interchangeably, collections and data sets. Same with granules and files. So when we use the search functionality in earthaccess, we're going to query against NASA's common metadata repository in just the same way that a graphical user interface like Earthdata search does. So we're going to create a query object. I'm going to give it a keyword ISAT2 for the ISAT2 laser altimetry mission. So we're going to use earthaccess search, data sets, and we're going to give it a keyword. ISAT2. Just look at that, looks good, and see what we get. So let's see how many returns we got for that. So we got 80 results or 80 returns for that query, meaning there are 80 data sets that have the keyword ISAT2 associated with them. So we're going to take a little peek at some of the metadata. So what gets returned from our query is a list of data set objects, and these data set objects have a number of methods associated with them. And we're going to use the summary method to grab some information about the objects. And then here's where we're going to use that pprint or pretty print helper library to display the information. Okay, so a bit of typing here. And we're gonna just look at a couple because we don't want to overwhelm our display with 80 metadata entries. So we are going to use this summary method to display just some information about the data sets that we surfaced. And then these arguments are just helping the readability. And let's see, print. All right. So, phew. All right, so let's just take a look at some of the metadata elements. Gives us some useful information about the data sets that we surface. So we have a section here with cloud info. This gives us some information about where the data are stored. This becomes more important down the road when you're wanting to access the data directly in the cloud via streaming. We can see the concept ID for the data set, which is a unique identifier that each data set has in the NASA Common Metadata Repository. You can see file type, which for this particular data set is HDF5. Get data section gives us some useful links with some things that can help support data access. We get the short name. This one's really important. This is like an abbreviated name or almost like a nickname that for this particular data set that NASA Earthdata sets have these. For this one, ATL06 is an ISAT2 data set. It's the land ice height product. And here, the one that was surfaced is version 7. Version 6, version 7 are the most recent version of this particular data set, but version 6 is still available as well. They're available, they have some overlap for a time after the data set versions up. So, all right, so that was steps 1 and 2 in our workflow. We authenticated and we searched for data sets that have the keyword ISAT2 associated with them. And now we're going to search within a data set for particular files. And so in this demo, I'm going to use ATL06, which I mentioned is the ISAT2 land ice height product. We saw before, so we use the method search data sets to look for data sets. And now we're going to use a method for searching for files or granules within a data set. And that is the search data function. And when we're using search data, we're going to apply various filters or search criteria to help narrow down our results. In this example, I'm going to use a bounding box to search for the land ice height data over the Juneau ice field in Alaska. And I'm going to restrict my data search to data collected during March and April of 2020, just to narrow things down a bit.
Mikala, this is Steph interrupting to say, there's about 3 minutes left in your presentation, folks. Mikala asked us to give a reminder. And so this is the joyful timekeeping. Go ahead, Mikala.
I will be very close to that. If I go to 4 minutes, is that okay? 4 or yeah.
You do what you need to do. Yeah.
Okay, we're really close. All right. So now we're gonna query. Yeah, and thank you for the reminder. I did ask for that. Time check. All right, so we're gonna query within our data set now. And so we're gonna use earthaccess.search data. We're gonna give it some search criteria. Gonna do the short name. I decided that we're going to use ATL06 for our example. We're gonna search for version 7 since I know that's the most recent version of the data. I'm gonna give it a bounding box in a particular format. Here I'm supplying the corner points of the bounding box, and the order is west, south, and then east and north, and these are latitude and longitude values. And then we're going to give it a temporal range. So here we're going to go 2020. Oops, I need one of these. 2020, and we're just, example we often use is just for a couple months in March and April. All right, so that looks right. Yeah, that's all we're gonna tell it. All right, okay, well, that was good. That ran with no errors. And let's see how many results we got back from that particular query. So we got 4. That means we have 4 granules or 4 files that fall within those search parameters. So we're gonna use this display function to get a little preview of files, those files that matched our search criteria. But this is just a Python library that helps us get a little peek. So I'm going to use a list comprehension just to do this. And this allows us to take a look at a little bit what these data are before we start interacting with them, before we either download them or open them. So we can see file names, file size. Over on the right hand, you can see these little thumbnail images, gives you a little bit of a peek to what the data might look like. Yeah. And the last, let's see, where did my, might have to, sometimes these get a little buggy. The Jupyter notebook scrolling can get tricky. So, okay. Just a quick recap. We authenticated, searched for data sets using a keyword. Then we searched for data files within a data set using our search parameters. And now we're going to go ahead and use earthaccess to download the data to, in this case, I'm going to download the data to this local hub space. So my instance in the hub. You could also do this to your local machine. And I think the advantage of working in the hub and the power of using earthaccess will really be demonstrated later. Also, when we'll see examples of accessing the data in the cloud directly, like a direct access pattern next to the data in the cloud. So, but for now, for this, we're going to just download here. And so to do that, we're going to use the earthaccess download method. And I'm going to download our results. And like you saw before, I'm going to tell it just to download the data right here so we can see it happen. This takes a few seconds. We should see those pop up over here, just in my directory right here. And yeah, and that's it. Just a little note here. earthaccess also enables the direct cloud access, which we'll see examples of. Yeah, and just to recap, those were the 4 basic steps that we use: authentication, searching data sets, searching for files, accessing, and just like Amy mentioned, you can use earthaccess and get data in just 3 lines of code. So super simple and powerful. That's it.
Thanks so much, Michele. And yeah,
That was my time.
You're great. Great. Yeah, it's awesome to see how you can download data using earthaccess. And then after our break, Andy will show how you can stream data with earthaccess, which is super. Yeah, to reiterate that, that's so great. There is a question in the chat already, but I'm wondering if other folks have questions ready, or if we want to have more of a discussion around Angela's question. So Angela, you're welcome to say out loud your question and kind of your thinking, and we can discuss.
Yeah, thank you. I like I said, I'm new to this. So I'm just trying to figure out, and I appreciate the links that have already been sent in the chat, just how to discover what is available. And then also, I know you had mentioned, there's a newer version available. It seemed like you just kind of knew that. So I was trying to figure out how to get that information ahead of time so that you're most informed when doing these searches.
Yeah, that's a really good question. I was working with a lot of information that I already knew for sure. I think one really nice way to do search and discovery, you can do that. If you're willing to get out of your programmatic workflow a little bit, you can use the NASA Earthdata search website, which maybe somebody's putting a link to.
Yep, Saber's been sharing that in the chat. Yep.
Nice, excellent.
Saber.
That's a great place to do some search and discovery, and you can get information like that about what is the most recent version of a data set. At NSIDC, like the different data archive centers who catalog the data and manage that. We have a lot of resources about the data sets that we manage, and some of this will change location a bit as the web unification that Michele was talking about continues to happen. But like NSIDC, we have our website, and for all of our data sets that we archive, we have data set landing pages. On these data set landing pages, there is information about the data set version. It indicates whether it's the most recent version. There are whole user guides that tell you about the data, how to use them, and then all sorts of technical supporting documentation, and then links to tools and resources. Maybe I'll put in the chat like an example. Hopefully this is who wants to format it like so. Here's like if you go there, let's see if that link works without like all the prefix. Yeah. So if you click on that link that I shared in the chat, for instance, it gives you an example of one of our data set landing pages. So yeah, there are a lot of resources, the NASA Earthdata website, NASA Earthdata search, and then the different data centers curate these pages for the data sets that will be really helpful.
Great.
Yeah.
Thank you. There are some questions in the chat. I'm seeing Alexi's about the Jupyter Hub, which I'm responding in chat, Alexi. I'm also seeing Anastasia's question. Is all Earth data available to retrieve with earthaccess? Also, is Earth data planned to be available through earthaccess? So I wonder if you could speak to that, Mikala or other mentors.
Yeah, all of NASA Earth data are available via earthaccess. So as long as it's in the NASA's Common Metadata Repository, yeah, you can access those data. Thanks, Sandy. I see you.
And Alexi had asked about Jupyter Hub, and I've responded, but I don't, if you had follow-up questions or something else wasn't clear, Alexi. I would say the 2I2C Jupyter Hub, where Mikala was working today, is a compute environment that's near the data, but it's not actually storing NASA Earth Data's archives, if I understood the question correctly.
Yeah. I'm trying to look through chat too.
And Tim has a question. Tim, would you like to unmute?
Yes, hello. Thanks for the opportunity to ask a question. First of all, I'm totally new to earthaccess, so I was really open to what information will be given today. And so far, it's very interesting. Thank you. And I have a very specific question, a specific use case. So I'm a professional in the plant variety development area. So I work with field trials, and I began a few years ago to use UAV assisted data collection. And so for me, it's very interesting what opportunities are there via satellite images to, let's say, for example, choose a correct field site where I can do my tests on. And to me, I was asking myself, does earthaccess give me an opportunity to choose a site and to make an observation or a selection based on several arguments like how's the soil texture and surface structure variability, for example, or are there any compaction related surface signatures and aspects like these. They are very interesting to me. And does earthaccess give me some help here? And how could I incorporate earthaccess into this workflow?
Yeah, that's a really good question. And anybody feel free to hop in there too. Andy Barrett, Amy Steiker.
And if it's, sorry if I interrupt again, if it's
Yeah.
too early in this session or maybe for the next session, it's okay if you postpone this if I'm too early for specific questions like these.
Yeah.
You know, it's a great question. And we have folks here with good responses to it. We're 1 minute away from our break. So I wonder if we should take our break and then come back with a response to that question. Does that sound like a good plan? Just in case people had planned for the break, but are curious for the question.
Of course, I don't want to be the one that
No,
stops
it's a
the
fantastic
break.
question.
Okay.
Well, why don't we take our break then? We'll give Mikala and Amy and Michele from this morning, or sorry, from the first half, a round of applause, and we'll take a break for 15 minutes. Steph, please. Oh, sorry, you're clapping. I thought you were helping. We'll keep the Zoom open, so you're welcome to stay here. People will be around if you have questions kind of in the chat or just want to linger, but otherwise we'll be back at 40 past the hour in whatever time zone you are in. Great.
And kind of to our next speaker. It should be Andy, I believe. Take it away.
I've just shared my screen, so hopefully everybody can see a picture of the polar stern.
Yes.
I'm going to cover what we build as a real world science problem and application of earthaccess. And I'm going to introduce a workflow using earthaccess that I used a while back to look for ISAT-2 data that coincided both temporally and spatially with the Mosaic expedition. You may have heard of the Mosaic expedition. It was a multidisciplinary campaign in which the Alfred Wegener Institute research vessel, the polar stern, was frozen into the Arctic sea ice starting in, I think, September, October 2019. And then the ship drifted with the ice and it was used as a floating platform for collecting information about the sea ice and the changes in the sea ice through the season, how the atmosphere was changing, and also how the upper ocean was changing, both in terms of biology, in terms of physical characteristics. And it yielded a huge amount of data that is still being worked through. But from a remote sensing point of view, this is a bumper crop of information, and we want to kind of be able to bring remote sensing remote sensing resources to bear and see how they compare with what's being observed and how they can help provide more information about what's going on. So what I'm showing here is a picture of the polar stern frozen into the Arctic sea ice at night. It's surrounded by instrumentation. We had weather stations. We had remote sensors on the ice collecting in situ data. So what I want to do is be able to find information about what we call the sea ice freeboard that is collected by the ISAT-2 altimeter. Altimeters measure the height of things above the Earth's surface, and freeboard is the height of either the sea ice or the snow surface above the local sea surface temperature. And we can get this using the ISAT-2 data. But I want to collect that data in tracks. And so I want to find coincident tracks with that data. So I'm going to switch to another clean notebook, relatively clean notebook, to demonstrate that, and then go through the coding steps that I use to find this. So I'm going to import a number of libraries, and earthaccess being one of them, but I also want to be able to read data and process data. So I'm going to be working with Python packages, pandas, geopandas, X-ray, which you've already been introduced to, and also I need to work with some vector data. So I'm going to import the Shapely library to do that. And then I want to produce some plots, and I like to use Cartopy, which is a mapping tool within Python, and Matplotlib for plotting. And what I'm going to do is load in a vector file, a GeoJSON file that has the Polar Stern cruise locations in that file, and then use earthaccess to go through that file and look for tracks that are close to the location of the polar stern on each day of its drift. So I'm importing those files, and then I need to, I've already said what the polar stern drift file is. That has the information that I'm using, but I'm going to use GeoPandas to read that. So I'm going to load it into a geodata frame using GeoPandas read file. And we're going to make use of autocomplete here. And I'll just, so we've loaded this file. We need to do some things to here to make the analysis work better. I have time, I have a latitude and longitude, and I have the speed of the drift and the course of the drift. I also have this number here called flow. That's there were 3 different ice flows that the ship moored to, so that's the number of those flows. And then we have this geometry here, which is the actual points taken from latitude and longitude of the ship. So I want to do some quick conversions here to convert the date time or those dates into actual date time objects, so that I can do some calculations using date time. And I want to make that the index of my GeoPandas data frame. So I'm going to set the index. And we don't need to include that in the data frame anymore. So we'll see what that looks like here. So now I have this is called a data frame, but you can think of it as a table or an Excel spreadsheet type presentation. We have latitude and longitude, all those fields that we had in that original file, and then I've now created this index along the time, which allows me to actually search by date for each of these points. And just to save time, we want to plot this just to get a feel for what the drift track looks like. So I'm going to copy and paste these commands in. So I'm going to plot this as a polar stereographic projection, in particular the NSIDC North Polar stereographic projection. So this is creating a projection object with those projection parameters for the polar stereographic projection. I'm going to then use matplotlib to create a base plot, set my extent here, which I know includes all the data. And then this command here is plotting the GeoPandas data frame. So taking each of these points here in this data frame and plotting them. Then I'm going to add some features like the ocean and the land so that we can actually orient ourselves. Takes a little while because there's quite a few points, but here you can see this is showing the different flows and the drift of the polar stern throughout time. So it was initially moored to a flow here. This was during COVID. The ship had to actually go and pick up a replacement crew. So it had to leave the flow and then moored to a second flow here, drifting out of the Arctic. But the drift was pretty fast during 2020, and so the ship was out of the ice, so it needed to go back into the Arctic and find another flow for the spring. So we can see what the flows look like. Now we want to utilize this information to actually search for some ISAT2 data. And the first thing we want to do, if you remember back to Michele's demonstration, is to actually log in to earthaccess so that we can do the search and download. And I have this set up so that earthaccess knows what my username and password is. If you're going to do this and you don't already have what is called an Earthdata login, you'll need to just go to the NASA page for Earthdata login and log in, or set that up, and then you can authenticate. Now, I'm going to use a slightly different search method than Michele, because I need to search for each day for ISAT2 tracks that are close to the drift trajectory. And so I'm going to have to do that in a loop. And I'm going to use a spatial search method that's particular to earthaccess and CMR called circle, which what it does is to search for data within a circle of a particular radius. And I'm going to define that radius as 20 kilometers. It's defined in meters, so that's 20,000 meters. And I want to store those results, and I'm going to store it in a dictionary, initially an empty dictionary that I'm going to call results. And then I'm going to loop through that GeoPandas data frame using a method called iterows. So what this does is go through each row of that data frame. It gets the index, which is the date, and then it gets all the other fields in that column and then we can feed it into an earthaccess search. I'm going to store that particular result, one result, in a variable called R. And we're going to do earthaccess search data. Now, I think Michele used a DOI. I'm going to use what is called a short name. And this is kind of like the shortcut to data sets, and you find these on the dataset landing pages that the DACs maintain. We're searching for ATL10, which I know is the sea ice freeboard dataset. we're going to set up a temporal range, and I've already I've just forgot to do something here. So in order to set up this temporal range, I need to set a start and an end date. And I already have the date from the index, but I want to search within 12 hours of that date. So I'm going to use a date time delta. This allows me to do date arithmetic. So I can subtract 12 hours from the particular date to get the beginning. And I'm going to set date end to be 12 hours plus the date. So once we've done that, we can do debug, and we need to pass it as a string formatted in the ISO format. I forget the standard number, but this method ISO format actually does that formatting for me. And this is where the power of using packages and libraries comes in, because it really just makes everything very simple. And now we're going to do this circle search, right? This is different from the bounding box that Michele showed, but we can get the longitude and latitude, which is in that data frame called fields. And we just pass it the radius. And I know that, as Michele mentioned, most data sets have at least 2 versions. The most recent version for ATLO 10 at the moment is version 6. They're still processing version 7. So we're going to search for version 6. And then this gives me a bunch of results if it finds something, but we want to store that back into the result dictionary that I defined earlier. But I don't want to store anything if there were no results in found for this particular date range and location. So I'm gonna test to see if there are any results by testing the length of R, which is actually a list. So we're saying if the length is greater than 0, then we have some results, and we're going to store it in results. Right. And if you're not familiar with Jupyter notebooks, there's a useful little magic command called time, which will give the time that it takes to actually search for this data. And we have a mistake. Oh, yes. There we go.
Also
right,
see in that line,
Oop.
Andy, you've got
Yep.
fields and field. In
Oh,
that line.
lovely. Thank you, Julie. This is called co-working and group programming, and we're getting some. What have I done there? There we go. And this will take half a minute. Now, while that's going, I can start typing the next line here. So there was a question, I think, about how can we work in the cloud and not have to download our data to our local machines or even into the cloud. And so I'm going to use a method called streaming to open files directly into memory. And I can do this efficiently because I'm working in the Openscapes hub, which is in US region, or AWS region US West 2, which is where the NASA data is. So I'm right next to the data, so I can have pretty fast access to that data. I'm gonna, because ISAT2 files are big and take a little bit of time to process, I'm just going to demonstrate with one file, but in this notebook, which is available in the GitHub repo, linked in the notes, there's some bonus material that allows you to open multiple files. So we're going to use this earthaccess.open method to stream the data. And that's already streamed because there's just one file. Now, this gives us essentially a virtual file object that allows us to work with it as if it was a file on our local file system. The ISAT2 data are HDF5 files, and I can use Xarray open data tree to work with that. HDF5 is what's called a hierarchical data format. You can think of it as essentially a file system within a file. So it has groups, and within those groups are subgroups, and within those subgroups can be more subgroups or data variables. And that's kind of a tree-like structure, and Xarray has an open data tree method to work with this kind of data. So we're going to open data tree. We're just going to open one file from this, and I'm going to have to add some keywords here to stop some errors being thrown. And I won't necessarily explain what these are doing because I don't think it actually applies. I think it's more a bug in the data tree code, and maybe possibly because the ISAT2 HDF5 files are quite complex. So we're just opening this file. Takes us a short while to open it. Again, these are big files, comprising six beams. They have, each beam has, in this particular file, 50,000 points within it. You can see here there are groups, and we've got multiple groups here about the orbit of the satellite, about the quality of the data, and then we get down to the information about the beams, and these are named GT 1, 2, 3, and they have a left and a right beam. And within that, there are other groups, and this one is the one that I'm interested in, freeboard segment, which has the actual height of the ice above the local sea surface. So I happen to know that the data I want are the latitude and longitude in GTL 1L, which is the first ground track with the left beam. And because I want to plot these rather than actually analyze the data, I'm just going to grab every 1,000th point, so that it makes plotting easy and processing easy. Now, what I've done here is to take the longitude and latitude data and put it into an array called longitude and latitude. And to make plotting easy, I'm going to create a GeoPandas data frame from this. And I need to do two things for that. And so I create what is called a line string, which is essentially just a vector line. And then I pass create the geodata frame using that line. And I know that longitude and latitude are in WGS 84. So I'm using the EPSG code 4326 to tell the geodata frame what the coordinate reference system is. So this is now a geodata frame. It has that particular ground track from the satellite in it. And we can use the same plotting routine as we used here.
Andy?
Yep.
Andy, this is Julie, just a time check. We have
Yep.
about 5 minutes left for this
Okay.
section.
Okay, this is the finale. So drum roll,
Okay.
please. Yeah, so we're using that same plotting routine, but to that I'm going to add plotting the the track. We know that the track's in WGS 84. We want to convert it to the projection that we're using, which I know has the EPSG code 3413. And then we'll plot it to the same axis. We're going to choose our color, which we're going to say is crimson. Don't want the markers to be too big. And we'll give it some transparency just so that it doesn't completely obscure the information below it. And there we go. We've gone through, we've searched for ISAT2 tracks for a particular location around the polar stern drift. We've then taken one of those tracks, grabbed some coordinates from it, and created a vector line that we can then plot on the map. This notebook is in the repo. I have some. I'll just scroll down to the bottom here. It has kind of explanation for what I've done, and at the bottom here, I've got some bonus material where you can plot all the ISAT2 tracks. I need to figure out some of the bugs in there, but it will currently do the first 20 of those that you can see plotted here. And also I've asked some questions to kind of as a little challenge to you and also to help you get your feet wet with using earthaccess and X-array. And with that, I will stop sharing. Thank you.
Super, Andy. Thank you. What questions do folks have for Andy?
Can I just say that it was very interesting and nice use case, and I'm extremely inspired to getting into depth into this. And yeah, that's very amazing. And thanks you guys for sharing. Thank you.
Thank you. It's great feedback. Was there a specific part that caught your eye or caught your attention that you want to try?
Yeah, it was more expandable to work with the earthaccess. I was recently also experimenting with GeoPandas and transferring into different Cartesian projections. And yeah, it was just interesting to follow the process and try some things that I never seen done before. That's very, very cool. And thank you for the link.
Yeah, and I'll add that I used the circle method to search for data within a certain radius of a point. Michele used the bounding box. You can search by polygons, so define your own polygon. You can search for data that intersects with a line. So there's a whole bunch of different methods that allows you to do spatial searches to get your data. So you're not just confined to using a bounding box.
Yeah, that was actually also very interesting because, yeah, I thought it's only bounding box, and I saw on every type of URL searches through S3 as well that it's on bounding box mostly. So it was interesting to see as a circular. Yeah. Thank you.
Right. Well, super. Thank you so much, Andy, and for the questions. We are going to now shift to Danny Kaufman to share more about where earthaccess is going. And this is a preview of what we'll get into more in depth in 2026, most likely. So Danny, please go ahead.
Sure. Yeah. Can you hear me?
Yeah.
Okay, cool.
Great.
Cool. So I'm going to try to share this window, see if it works. Okay. Do you see a browser?
Looks great.
Cool. Okay. So yeah, I'm going to just I'm going to spend a few minutes talking about one particular way that we're broadening earthaccess. There are a variety of different efforts to improve the package, fixing bugs, making it easier to contribute, so on and so forth. That in the earthaccess community is improving in a lot of ways. This one particular way that I'm going to share on right now is called virtual data sets, and it's a way to improve the experience of the access part after you've done a search and you want to then work with the data. This is very much work in progress, so I'm kind of sharing a state of share the concept and the state of things and kind of the vision moving forward. So I'm Danny Kaufman. I'm at one of the NASA DACs, the Atmospheric Science Data Center, and I'm not the only one working on this. I'm going to be sharing this work that folks from a variety of different NASA data centers, along with the open source community, are working on. Okay, so the context for these virtual data sets is this particular challenge that researchers and other data users might run into, this bottleneck of downloading the data that may take quite a long time, and then the analysis that you actually want to do is maybe only for a small amount of the data that you ended up having to download. So here I have the quote: spend a whole day downloading data for 30 minutes, or a whole day downloading data for just 30 minutes of analysis. And this is a kind of one of a variety of different potential challenges with research of big data sets, where you need a data set and it might take a long time to download, but then even while you're downloading it, if it is a really large data set, you might run into storage limits, either trying to save those data to your disk, or working with the data in memory. If you're streaming those data and you're filling up the memory of the space, for instance, the Openscapes cloud computing environment that we'll be working with at tomorrow's co-working, I forget exactly how much memory is provided, but maybe 4 gigabytes or 7 gigabytes, and that's a decent amount of memory. But if you're working with a huge data set, you might run out of the memory at some point if you're trying to use an entire data collection. And because of this, you may end up finding yourself limiting your analysis to manage it. So you might only work with a smaller amount. You might only download a smaller amount just for practical reasons. And you may also have challenges if you're trying to share that with other researchers. So overall, you might spend more time dealing with these issues, less time actually doing the analysis and gaining the insights from those analysis, and you might limit the scope of your analysis because of these challenges. So some of these challenges are manifested even in or come about because of the way the data are stored when NASA is is processing the data from the instruments on satellites or suborbital missions and packages up those measurements into a particular file format and stores them in the NASA Earthdata archive. Many archival file formats end up storing both the raw data values and the metadata for those values, meaning bits of information about the data values themselves within a file. So this schematic on this slide is showing the traditional way these parts of a data file are stored in particular these file formats called HDF5 or NetCDF4. That's a hierarchical data format. Andy mentioned it just a minute ago. Many NASA Earthdata data sets are stored in this format, and they scatter the metadata, these orange chunks, these orange blocks, along with the green blocks. So when you're trying to work with these data to figure out what data values you actually want to access, many times you'll have to read this entire file to gather together all of the metadata, so that way you know where in the file to actually get the data. So if you need some small amount of the data from the file, you actually will need to download the entire file and parse all of that metadata to get even just one part of the file. More ideally, you would separate the metadata and use that more like a table of contents, like in a book where it's all at the front of the book. And if you want to jump to one section of the data, you would read the table of contents first and then jump to the section that you want. So here, separating the orange from these green blocks. Now, this particular approach to separating metadata from data values has been achieved and is being implemented in a variety of different ways to give more performance benefits when working with data in the cloud. This virtual table of contents is often termed the chunk manifest. So, and the reason why it's called that is it's a manifest, like in a ship manifest, like an inventory of what's being stored. And then the chunks are these green blocks, the chunks of data values. And in essence, this provides this orange chunk manifest, or the table of contents, provides ranges of bytes for all of the values within the file. So going from this analogy of the table of contents on the left to what it actually looks like in these virtual reference files on the right, these virtual tables of contents, where you have things like 0.0.0 in index for a particular chunk of data, and you have exactly how to get to it. You have a path to a file in wherever it is. You have the how many pages in, or the offset, how many bytes in, and then the length of that chunk. And using this chunk manifest approach, when a reader goes to a file, it can access parts of the file much quicker. If you need the whole file, it's going to take roughly equivalent, because you're going to have to download the whole file or parse the whole file either way. But if you only need small amounts, which in a lot of analysis cases you do, then you can get access to those particular parts of the data file much quicker. The leading format that implements this is called ZAR, but now what we've been able to do with a lot of the NASA Earthdata is provide this ZAR-like access using this table of contents concept to data collections that are stored in these archival formats of NetCDF and HDF that aren't in the ZAR format. And so without having to actually convert the data formats, we can utilize tables of contents, these virtual tables of contents, to provide ZAR-like access. Okay, so how does this look in practice? I'm going to provide an example for some of the collections that have metadata already. So one of the collections that I have in mind is this air quality satellite mission that NASA launched 2 years ago and has been providing measurements over North America. And this particular satellite, along with many other satellite missions, has existing metadata, chunk manifest metadata stored in a format called DMR++. The acronym is not important. It's essentially a chunk manifest written in a particular format. But this format was created for OpenDAP, if anyone is familiar with OpenDAP. If not, that's okay. The essence is that this is chunk manifest metadata that's stored separately from a file. So in this case, for this particular mission, there are NetCDF files and there are DMR++ reference files associated with each file. And what the parser can do is read these DMR++ files and kind of generate the table of contents from those without actually touching the NetCDF files. So what this one particular workflow of using virtual data sets involves parsing each of the DMR++ files that are in the NASA Earthdata archive, combining those together into a larger chunk manifest, larger virtual table of contents for all of the NetCDF files associated with this satellite instrument mission. Now, this larger table of contents can then be stored in a variety of formats like JSON, Parquet, or IceChunk. These each have slight advantages or disadvantages. Conceptually, they're all equivalent in the sense of storing this large chunk manifest, this table of contents, to a whole array of NetCDF files. And then this combined reference file is the thing that can be held in memory. And this reference file will be much, 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 much smaller than all of the NetCDF files if you were to hold all of the NetCDF files in memory. By then reading this table of contents, we can then jump to the NetCDF files and extract the part that is most useful. So for instance, if you wanted to generate a time average map of values, this is showing right here. For no particular reason, this is showing the Chesapeake Bay and the US East Coast. But this was an image generated from a year's worth of data, generating the time averaged values for each point in this map. And we did not need to read all of the NetCDF files, or did not need to read all of the data within all of the NetCDF files to generate this map. We were able to read the combined reference file, jump to each of the parts within each of the NetCDF files, and then compute the average from those parts. Okay, this was sort of a long roundabout way to get back to earthaccess, to explain this whole concept of virtual dataset access. And the reason I kind of did this workflow is to show how earthaccess sits within the ecosystem of a variety of different open source tools. And what is being built for earthaccess is this smart integration with these other tools. By utilizing these other tools and then providing access that works well with that ecosystem. So in this case, each of these steps within this process, we have the DMR++ files that are a format managed by OpenDAP. These DMR++ files are parsed by this Python package called virtualizar. These are combined using the Python package Xray, which we've heard a couple of times already. And then earthaccess is still in the process of figuring out where does it sit to best make it easy and user-friendly to get to this step where you're just accessing just what you need and making it quicker to get to this kind of analysis step. And right now, earthaccess, excels at finding the files and the DMR++ files, which are right next to those files. And we're working next to kind of allow this read the read reference part to kind of sit in there really nicely. There's been some prototyping, and this particular workflow I showed is demoed and is in the earthaccess documentation, using a prototyped function called Open Virtual MF Dataset, so Open Virtual Multi-File Dataset, and using the DMR++ files, we're able to generate that map that I already showed, but this was from the Tempo Air Quality Mission for a year's worth of data. I did some benchmarking, some estimating. It would take about a whole day to download all of those data files on the system that I was working on. It took 10 minutes to generate this file because I didn't have to download all of those files. So this goes back to that question that was asked about working with files in the cloud and not having to download them. This is what Andy showed, is showing we can already do that, and this is sort of taking the next step to make it even faster. And what I showed with the different kind of components, this is a work in progress and a negotiation and coordination between these different open source packages and in the open source community. And we're making it a very flexible architecture. We've already moved around pieces from earthaccess to virtualizr and vice versa in order to make the APIs most user-friendly. Okay, so this is my last slide. Where this is going is to streamline this in a number of different ways and like basically make it more robust. And some of those are still prototyping stages and testing and getting things to work. The goal will be to be able to read different formats of virtual data sets, virtual reference files, whether they're formats called chunk and ice chunk, and these would be things that NASA Earthdata may likely provide, and then earthaccess could read. There's work going on to figure out how to manage the credentialing parts to make the credentialing just as easy as it is right now with earthaccess, where the authentication step is just one line of code, and we don't want to. We're trying to figure out ways to avoid making that more complicated when using virtual reference files. Supporting data sets that don't have the DMR++ files, that's also work that's underway. And then, as I already mentioned, maintaining the user-friendly API. There's talk about different kinds of new functions that may or may not get added to the API, or maybe most of this can be hidden from the user and just provide the fast experience whenever it actually is available for those particular data sets. So there you go. That's my brief survey of the virtual dataset landscape and how it interacts with earthaccess. So that's all I have. Thanks.
Thank you so much, Danny. It is so exciting to see all the work you're doing and collaborating across these communities. So thank you so much for sharing. We are going to not have a discussion at this point and shift this directly to Celia Wu, who is going to share about our resources and contributing to all of this work. So take it away, Celia.
Thanks, Julie. Do you mind driving the slides?
Yes, absolutely.
Thanks.
And I'll also say it's only a time issue of why we're not having a discussion with Danny, but please put any questions in the chat, and we can also follow up with coworking tomorrow. Okay. Amazing how quickly time flies when we're learning about earthaccess together. Okay.
Thank you, Julie. So I hope hearing about earthaccess and virtual datasets got you excited about getting your hands on both of them. And so I will be talking about something to help you do that and get you excited for hands-on work tomorrow. I'll be talking about the cookbook and open communities I'm Celia O. I'm at PODEC. That's a physical oceanography deck. Yeah, next slide, please. So the NASA Earthdata Cloud Cookbook is one of the earliest resources by NASA Openscapes, and it's really a cornerstone of our work. It supports science research teams working in the cloud, or really also outside of the cloud as well on your own machines. And it's really a curated collection of tutorials that have gone through many iterations, and we continue to iterate on. A lot of them come from live events and workshops that we've held, and then they've been refined and archived in the cookbook. And it's for self-paced learning, as well as the live workshops that they debuted in. Everything in the cookbook links back to its source in the GitHub repository. So since all of these resources are kept in the GitHub repository, it can be under active and open development. And we're always like welcoming feedback and editing from users and mentors alike. So next slide, please. And so the approach of the cookbook and the community surrounding it are inspired by, I want to mention the Carpentries, if you recognize that organization that provides data, library, and software like coding workshops and training. They also provide instructor training, and their philosophy in making coding materials and workshops is something that inspires us. An example is the figure on the right is how we think about and structure all the materials. Like there are tutorials which are separate from the style and purpose of how-to guides, and which is separate from explanation and reference. Just thinking about what is the target audience and what do they need to do what they want to do. And we're always, just to summarize, the principles that we're striving towards involve that we are all always learning, and we want to provide access for all. Next, please. And so with that in mind, welcome to the NASA Earthdata Cloud Cookbook. We really mean welcome. Next. And so part of putting the principles into reality is that if you notice in the cookbook, the contents bar on the left has a how to contribute section. And on each page, on the right-hand side, there's a link to edit this page that takes you to GitHub, as well as view source. So you can view the repository material that is that is the source of the content for this page. In this example, is just the home page, but this really goes for every Jupyter notebook that we show in the cookbook, and every how-to guide and figures as well. Next. And so one thing that we can do tomorrow is contribute together to the cookbook and earthaccess. Who can contribute? Anyone can. Usually, because of the content, that'd be anyone with interest in data usage or science, NASA Earthdata in particular. So it's not just researchers. I want to throw out there, you can be an intern a student of any kind, undergraduate, graduate, teachers as well. And all the contributions go through, just depends what the process is. It can go through discussion or approval with whoever's maintaining the cookbook. And even if, it's not completely decided where they fit in perfectly, it doesn't have to be perfect. We have an in development section or a parking lot for materials. And so I hope this encourages you to contribute, because you're really welcome to. The cookbook authors really mean that. And if you have work or progress, something that you find valuable to you, there are others who will also find that valuable to see. And something that we, the cookbook authors and Openscapes mentors, always tell ourselves is, you start small, and whatever you have, it's good enough. And it's we really encourage everyone to build your skills and share those in the cookbook or by contributing to the cookbook and earthaccess packages or documentation. And we are all learners together. Next, please. Yes, so what do you need to contribute to the cookbook or earthaccess? For the cookbook in particular, it just takes a basic, install Git if you don't have it already, and probably get a GitHub account, install Quarto, and a summary of the steps below is clone the cookbook, install Quarto, and you can already, just from cloning the cookbook, make your own preview of it. And if you want to edit, then you write in sort of a language called Markdown that is relatively simple to understand. And this can be demonstrated, or like we can work it together during tomorrow's session. Next, please. Right, and so it's for the NASA Openscapes community, it is not just the cookbook that is a center of resources. There are related cookbooks and communities as well. First one of which on the right-hand side is earthaccess that we talked a lot about. Earthaccess is not just the development of the package, but there's also documentation that is a community effort. And then two other related cookbooks are the Atmospheric Science Data Center, or ASDC cookbook, that separates materials by mission. And another one is PODAC cookbook for physical oceanography, which is modeled after the Earthdata Cloud cookbook itself. And so these are all related communities. Next. For example, each of them are in the same spirit, welcoming contributions. So this ASDC cookbook has a contributing guide and emphasizes even the guide itself is a draft and under active open development. Next. In the same vein, the PODAC cookbook has how-to instructions for contribution. It might differ, each of these communities might differ slightly from each other just because of specifics on how they are maintained and who maintains them. But they are all very similar and welcome questions. Next, please. An example for contributions to these cookbooks. First is for the PODAC cookbook, we had an intern a few years ago, Ayush, who attended the earthaccess bi-weekly hack days. And his intern work resulted in completed contributions and related work that is still ongoing. And his materials live on in the PODAC cookbook, which is linked there. Another one is the Openscapes cohort of the champions in 2023. And one of the participants was the GeoWeaver team. And Ji-Heng Sun contributed. You can see their team's contributions linked there in a GeoWeaver workflow demo, and that lives in the Earthdata Cloud cookbook. So please go check those out. Next. Yeah, so come on over, check out earthaccess and its documentation, check out the cookbook and the spin-off cookbook by the other DACs. And also feel free to come to any, or all of the earthaccess hack days and check out the events. We have one-time events at HU, conferences like ESIP and other workshops. Next. So for all the events mentioned, you can find them listed in the link in the orange box, summarized there. So an easy to find place for all of them, as well as the Openscapes and cookbook links. Thank you for being here, and hope to see you trying all these things out tomorrow.
Great. Thank you so much, Celia. What a wonderful way to end this session here today with such a welcome and overview of resources going forward and an invitation to contribute. Thank you. We are at the end of our session today. Steph.
Martina has a really important, valuable question in the chat. This is a lot of new information to take in. How can people make sure they're ready for tomorrow? You know, do they need to install anything? I think my answer is you're ready. Show up tomorrow. There will be like helpers, breakout rooms for different topics. You are ready. Just show up in Zoom tomorrow.
Yes, thank you so much, Steph. And that's a perfect primer here for me to screen share the closing. We've covered a lot, so much, Martina. You're not alone. And to prepare for co-working tomorrow, you really just show up. That's all you need to do. We have time to do anything and install anything ahead of time. We've mentioned the Earthdata login today. That's something that we can do quickly together tomorrow too. It's not anything you need to do in advance. We'll give you Jupyter Hub access tomorrow and introduce you to how to use it. I think that let's see, continued involvement. You've heard about resources will be on our link on the Champions page and YouTube. We appreciate your feedback and have this survey that Steph will also put in the chat. If you have any pressing feedback for us or now or in the future, we'd appreciate any questions or thoughts you had about earthaccess or about how we're teaching. We end Openscapes calls with quick tips of the day, open science tips of the day, and I thought I would demonstrate a quick keyboard shortcut for navigating in your browser window between tabs. So if I press the keyboard shortcut Control Tab, you'll see that I've switched to this other tab in my browser. And if I do Control Shift Tab, I can go the other way. So you can, these are little ways you can move back and forth. As you're learning to use the Jupyter Hub and look at the cookbook at the same time, that can be a handy keyboard shortcut, and we can practice that together too. So we will end on time. Really appreciate all of you for being here, all of the amazing presentations today. NASA mentors have been working for years together to present and develop so many of these things. And we just really, it's a joy to work with you all and really appreciate all that you do. So thank you. We'll see you tomorrow.